let's do another example. And this one is the one with the exception. So for this one, we are talking about a wire, right, with a linear charge density of lambda. Do you remember what was the electric field at a distance r for this object?
Lambda over 2 pi epsilon 0 r. I don't remember if pi was 0 or not.
Why you went there? Yes.
I'll do my stomach.
Okay. They want you back. So lambda over 2 pi epsilon 0 r. Do you remember this result?
Yes.
Now let's find the potential at that point. Let's call this point A and try finding it with respect to B at infinity. We will run into a problem very, very soon in this particular problem. So at a distance x, so let me call this r and let me call this x. This is x and dx is in this direction. So I can just write Vb minus Va is integral a to b e dot dx. Right? Any problem here? Yes.
Do we have to memorize this?
This one?
No.
No. This one, no. You don't have to memorize anything is an overstatement. But you shouldn't write it just like this, actually. You shouldn't memorize it. It's a bad thing to memorize it because in the exam, if you write it down like that, it's not a good thing. You might lose some points because then where did you get it?
So we should apply
You should apply Gauss's law to find it. I'm just saving time for you.
Because I didn't, and when you ask this, I cannot say it's this. I have to apply Gauss's law.
Yes, you have to apply and figure it out. So I'm skipping one step here. So Vb minus Va, if we are talking about Vb being at infinity, then this integral becomes, it goes from r to infinity, and I have lambda over 2 pi epsilon 0 x dx, right? As you can see, I end up with an integral that looks like this. Although it goes slowly, it does go to infinity. Do you see? Because integral of dx, integral of 1 over x is ln x, and when you define ln x between infinity and r, you get this ln infinity problem. Do you see the problem? This is the problem. So instead, just for this kind of cylindrical geometries with infinite charges, you need to define B to be not at infinity but at some far distance or close distance, doesn't matter, at some r0. Okay, so this is at some r0, could be closer to the wire, could be further away. You need a reference point. Okay, and let's say you have a reference point, then you just integrate until r0. So you need another parameter here. So this becomes r0, this becomes r0, and your result becomes what? Yeah, and I define VB to be 0 over here. So ln, you were saying yes, negative lambda over 2 pi epsilon 0 times ln r0 over r. Very good. So v at a distance r is lambda over 2 pi epsilon 0 ln r0 over r, where r0, this is the result where v r0 is obviously 0, because ln r0 over r0 is ln 1 and ln 1 is 0.
Are we assuming VB is 0 or is
We-
it 0?
We are assuming VB is 0. We are setting the 0 of the potential to some arbitrary distance r0. Okay, we have to do it because otherwise we don't have a reference point, proper reference point in this particular case.
John, could we choose on top of the line, infinite line?
No, because then you have ln 0 problem,
Yes.
which goes to minus infinity.
Okay.
You see, it has to be in between. Very good questions. So far, so good. We can move to a new, sort of a new topic. Equipotential surfaces. So basically, equipotential surfaces are surfaces on top of which potential is equal. Right? So for example, if you draw electric field lines, if you remember we drew the electric field lines before, they would look like this, right? So no. Okay. So what is equipotential surface? It's a surface where potential is the same. For example, this surface. What is the potential on top of that surface? Zero. Very good. Why is because whenever nothing is given, the answer is probably 0, right? I usually have a 0 person in the class who says 0 when I point to him or her. You can be that person from now on. It's yes, no, it's 0. There you go. So here it's not 0. Here it's not 0. So here it's more plus, here it's more minus. But notice that I drew it intentionally in a way that it's always perpendicular. Do you see? And that is indeed the case. Now, why electric equipotential lines has to be perpendicular to electric field lines? Because if we are talking about equal potential along this line, it means that there is no potential difference along that line. If you have no potential difference, you have no electric field. Okay? If you have no electric field along that line, then all electric field has to be perpendicular to it. Does it make sense? Yes? So the equipotential surfaces look like this. In this particular case, they look like this, and they are always perpendicular to the surface, to the electric field lines. So far, so good?
Yeah, we saw the question on the previous lecture that we had a, disc or like
Yes.
with a hole in it, and we said on the surface outside there's 3Q.
Yes.
That means that there's 1Q.
Yes.
So there's a difference. How can this stay?
Okay.
Like this?
I see your question. Here's the thing. What I just said is that there should be no potential difference. I didn't say that there shouldn't be any charge difference. So the potential at this point and at this point is the same.
Okay.
Do you see the point here? So what you are asking, how can I have minus Q here, plus Q here, and no electric field in between? I'm trying to remind you that we were not talking about charge, we were talking about potentials. Oops. So when you have the same potential, which is the case in here, I have the same potential over here. Oops. I have the same potential over here, over here, over here, over here. That's why I have the same electric field, zero electric field within. Good. Speaking of potential differences, let's talk about potential gradient, which means difference. Potential gradient. Do you know the word gradient? It's like the slope, the potential slope. So, earlier we have seen that you can find potential from electric field. What do you need to do? You need to integrate the electric field. Now, if you want to find electric field from potential, what do you need to do? Take the derivative, right? How do you do it? Here's how you do it. Electric field is the gradient of the potential. I will explain what this funny looking triangle means, but you might already know what it means. So this gradient means del over del x in I direction plus j direction del over del x, del y, sorry, and plus k del over del z. You can see that these parts seem to be incomplete. They are completed only if you are, these kind of things are called operators. Operator. This one is a gradient operator. It has to operate on something. That's when it gets its meaning. And in this case, it's operating on the potential. So if you operate on the potential, then you get this. E is negative I del V over del x, negative J del V over del y, negative K del V over del z. That's what it means. You see, just like by integration, with a dot product integration, we went from a vector field to a scalar field. Now we are going, using this operation, we are going from scalar field to a vector field, right? Both is possible, or both are possible. Example. Let me say I have given you a potential that depends on x and y, like this. Find the electric field at every point on x and y. So what do? You use this formula. So let me not rewrite it, but instead I will just duplicate it. So I'm going to use this formula. What do I need? I need del V over del x. What is it? 2x. What is del V over del y? 2y. What is del V over del Z? 0. Excellent. So electric field is negative 2xi, negative 2yj. That's the result. All right? So we have found electric field using the potential. Can you guess what I'm about to do? Just wild guess.
I think you are going to try to find the equation for V and then you will do this formula.
Something like that. Very good. So I'm going to try solving. Do you remember we had a solution for this system? Let me say this is X and this is R and this is a ring. Did we find the potential for this ring today? Yes, we did, right? What was the potential for the ring? Söyle. Very good. Everybody agrees? Yes? Now we are going to use this equation over here. E is equal to negative I del V over del X, etc. Now we have X, Y, Z again, but our potential only depends on X. So we only care about X. The others, so del V over del Y is 0, del V over del Z is 0. So my electric field is going to be simply negative I del V over del X. Do you agree? What is del V over del X? It's KQ del over del X 1 over X squared plus R squared square root. Do you remember how to take the derivative?
To the numerator first, and then you get the power to in front of the function.
Yes.
Then you get it back, and we also need to take the derivative of
The inside.
the
Exactly.
chain rule.
So this is so we use chain rule here, exactly. So this is like f of g of x, right? So what we are going to do is when we take the derivative of this one, we are going to use the chain rule. You are all familiar with the chain rule? Yes? So what we are going to have is, let me just go one more step here. This is basically del over del x of x squared plus r squared to the power of negative 1/2, right? So negative 1/2 comes in front, right? And then you have x squared plus r squared, negative 3/2. Is that correct? Yes? And then multiplied by 2x. Very good. Then, if I want to write E equals minus I del V over del X, it is simply minus I times, let me just take some cancellations here, minus x times x squared plus r squared to the power of negative 3 over 2 plus the thing that I put outside, KQ. Did you follow this? So the electric field is KQX over x squared plus r squared to the power of 3 over 2 in I direction. Do you see we got our previous result back starting from potential? So if you are more comfortable with dealing with scalar integrals and then taking the derivative, then you can do this kind of problems using this. If you get confused with directions and what cancels, what cosines or sines are doing there, so you can do it like this.
But sometimes, due to the lack of symmetry, when we are having scalar things, things get complicated. The integral becomes unsolvable to a person.
Sorry. This is, let me just, I think Siri tries to find meaning in what you are saying.
I don't remember saying HD.
Exactly. Tell me about it. Sorry, tell me again.
I mean, sometimes using the symmetry to make our calculations simpler is necessary.
Yes.
So, I mean, if we always try to take the potential first, find the potential first, there we will definitely encounter problems that our approach will be unhelpful.
I see. Yes. So let me generalize this statement. Use all these methods that I have taught you with care. Be careful, okay? Whether that method is really applicable there or not, okay? This is a general statement. Alrighty. Let me give you a homework which will not be graded, but you can just look at the expression for the disk, right? And see whether you get the correct answer there as well. So you have the expression for Vx of the disk, right? Take the derivative and see if it gives you Ex of the disk, right? Okay. And we are done with this chapter. Okay? Any questions? Comments? Ideas? No? Let's move to the next chapter then. Chapter 24, Capacitance. We will use a lot of concepts that we have learned in the previous chapter here. So you can think of anything that has two terminals that hold charge together as a capacitor. So in general case, we are thinking about two conductors. This one is a conductor, this one is a conductor. And you basically charge one side plus Q, the other side minus Q. And it can hold the charges like this for a certain amount of time. This is a general view of a capacitor. Now, what do we want from capacitors? We want them to have, depending on the application of course, we want them to have certain kind of capacitance. Let me write capacitance. How is it defined? Capacitance is defined as the voltage difference, the charge divided by the voltage difference. The charge that it can hold divided by the voltage difference that you have to apply or there will be created because of that. And it is measured in farads. 1 farad is 1 coulomb per 1 volt. Okay? So far, so good. What we are going to do next is to find capacitance of certain geometries. Okay? And we are going to use some of the expressions that we have found from previous chapters. So we start with the simplest capacitor that you know of, which is called parallel plate capacitor. And you might even remember the formula for the capacitance of the parallel plate capacitor. Do you? No?
Epsilon 0 A over D.
Do you remember this? For a parallel plate, ÖSS, YKS, what is it called for your year? YKS, yes. Okay. So let's actually, as far as I remember, this is never derived in high school, right? So let's derive it. Now, let's say I have parallel plate like this. And there is some distance here. There is some area of the capacitor, plus Q here, minus Q here. So you can look at this system as this system that we already discussed. Do you remember this system? And we already discussed that the electric field outside was 0, and inside it was sigma over epsilon 0, and not sigma over 2 epsilon 0, right? Not that. It was sigma over epsilon 0. What does it tell you about the potential difference between the points A and B? So let's go from A to B. VB minus VA is equal to sigma over, so let me just write it down as an integral, E dot dl integral, which means negative of the electric field sigma over epsilon 0 times d, the distance. Okay? Which tells you that VA minus VB, which is the difference in the potential, it's sigma times d over epsilon 0. And sigma is Q over A, and epsilon 0 is here, and d is here. So the potential difference, VAB, is this. And the capacitance is defined as Q over VAB. So what is Q over VAB? Q over QD over A epsilon 0, which is epsilon 0 A over D. So let me write it down in full glory. Capacitance for parallel plate is epsilon 0 A over D. Yes? Good? So this was parallel plate. Any questions? What if I have a spherical capacitor? Let's have a spherical capacitor. This time, I have a plus Q inside, let's say, minus Q outside, so both of them are conducting shells. So both of them are conducting spherical shells. Of course, you might ask how this one is charged. There might be a wire that comes out of this one somehow. Or maybe people are living here and just charging this part and charging this part. Maybe it's a huge thing. Why do you care? You never cared. I started caring, and you shouldn't. Okay? Plus Q, minus Q outside. So I want to find the capacitance. How would I find the capacitance? Well, I need to find this difference in the potential between A and B. So if I express the potential difference in terms of these Q's, then I'm done. Right? Can I point something at you? Like for the parallel plate, notice that the capacitance was depending only on the geometric factors. Okay? So it doesn't depend in charge or voltage that you are applying. This is not the case in real world. In the real world, maybe applying voltage would change your geometry, right? But idealistically, it only depends on the geometry. And here it will be the same case again. Well, let's find the potential difference. VB minus VA needs to be negative integral of E dot dx going from A to B. And what is the electric field in between? You can find it using Gauss's law, x dx. So E times 4 pi x squared must be Q enclosed over epsilon 0, right? So VB minus VA is negative integral RA to RB Q over 4 pi epsilon 0 x squared dx. Did you follow all this? Yes? So this tells us that VB minus VA is Q over 4 pi epsilon 0 and then 1 over x to be evaluated at RB and RA. Right? Let me reverse it. VA minus VB, which is VAB, is Q over 4 pi epsilon 0, 1 over RA minus 1 over RB. Right? And the capacitance is Q over VAB. That's why this is simply Q over this whole thing. Duplicate, put it here. So after some algebra, you get 4 pi epsilon 0 RA RB over RA minus RB. No, RB minus RA. You see, it only depends on geometry again. Yes?
Can you define capacitance by words?
By words?
Words, yes.
Yes. It's amount of charge that a capacitor can hold when you apply 1 volt across it. Okay? Very good. Any other questions? Yeah, no? Good. So there are some extreme cases for this particular question. What if RB is infinite? Let's take RB to infinity. Then what do we have as a geometry? We just have the middle circle. We just have a plus charge on top of a spherical shell, right? So it turns out that I was lying to you over here, saying that capacitors are usually two conductors sitting like this, A and B points. Turns out that just one conducting spherical shell can be considered a capacitor, right? But you are imagining that the other plate of the capacitor is at infinity. Okay? Good. So in this case, when RB goes to infinity, notice that so C was 4 pi epsilon 0 RA RB over RB minus RA. So RB going to infinity means that this will go to 1. No, not 1. Let me just write it like this. This will go to 1. Right? So then C as RB goes to infinity becomes 4 pi epsilon 0 RA. Turns out that just spherical shell by itself is a capacitor with a capacitance of 4 pi epsilon 0 RA. To use my trademark sentence, are you happy? Yes? Beyond happy. Ooh, good. Okay, the last part, right?
The problem is if we have only one shell, how do they go to
How this is a capacitor, right?
is this a circuit? Like is it in a circuit?
Let's say it's in a circuit. So you are holding one edge of the circuit with the ball, right? The other is in Mars. The other plate is at infinity. Okay?
There is no relation with electric potential.
Why there is no relation with the electric potential?
At infinity, do we still have it?
Yes, you do. So, what does it mean practically? What does it mean practically? Let me tell you what it means practically. Let's say, have you heard of this Van der Graaf thing? You put on it your hands and your hair goes up. This is quiz time. It is like that, just one spherical shell and you charge it with potential. Let me speak about it more later.